Hey everybody, and welcome to Images and Pre-Images Round 2 with Still Me. Today we're going to be talking about why pre-images and images don't cancel each other out. Remember from last time we talked about this function sine of x, and we looked at the image of 0 to pi over 2, and then we looked at the pre-image of this interval here, and we got not the same thing. So what we learned from that was 0 to pi over 2. So this set was not equal to the pre-image of the image of that set. And we're going to talk a little bit about why that happened. But first, what I want to note is that since this is 0 to pi, what we can say is while it's not equal, it is a subset. And in general, that result is going to hold. Your set is going to be a subset of the pre-image of the image. Why is that going to happen? So intuition. Suppose we have set A, and this is set B, and then we'll say this subset right here is S. We then want to look at where S is going to get mapped to. So S gets mapped to these two elements right here. So we're going to say that represents f of s. But then when we think about the pre-image of this, so pre-image of f of s, that opens the door for all the things that could map here. Everything that could map here, which would include certainly the things that we know mapped there. We already checked those guys. But it also includes this last element. And so there could be things that are mapping there that we didn't have in our original set S. So that's basic logic overview for why that works. It is not a proof. So let's go ahead and do a formal proof. So proof right here. We're going to let let's let x be an element of S, right? It's a set argument, and so we're going to start with something that is sitting in our set S. And we're going to chase it to this set over here. So if X is an element of S, that means the image of X is definitely in the image of S. That's just definition of image. Okay. But what that means is that X is a thing that maps to the set f of s, right? That's what this is saying. X is a thing that is going to map to f of s. We have a name for that. Oops, I picked up too much stuff. That is the pre-image. So that's just a side note for explaining why this next thing happens. So then X is in the pre-image because it was a thing that mapped to f of s. And then that's all it takes. Now we have S is a subset of this guy here. Okay. That's a little bit of work for flipping back and forth with images and pre-images with the theoretical stuff. We're going to do this. That's basically the theme of today, is doing this theoretically, flipping back and forth with images and pre-images using the definition. So if you're not quite comfortable with this yet, that's okay. We're going to do it again. Okay. But this is enough to prove our lemma that we have right here. And I would like to point out, just side note, stepping away, this was not a proof, again. However, pictures like this are excellent counterexamples. And so if you're ever like proving something isn't true, or you're trying to like disprove something, go with a picture. It's going to be much easier than trying to like define some sort of maybe crazy piecewise function, or being like, okay, well, x squared doesn't quite work, but maybe x squared plus 2x plus pi, maybe that one would work, or something crazy, just trying to build something crazy. Not a fun time. But oftentimes you know what needs to happen. You're like, oh, I know that I need two elements to come in like this, and then I need an element that doesn't get mapped to, if you're doing something with like one-to-one and onto stuff. So whenever you're trying to disprove stuff, especially involving like images, pre-images, one-to-one, onto, draw yourself a picture if you're trying to disprove something. I promise it's going to be a much easier time for you. Okay, gonna get off that chair. Back to the theme. This guy was just a subset of this guy. We proved that. So then the question is, why can't I finish the equality? Because of this element here. He goes back to two locations. So in order to prevent this funny subset business where it got bigger when we went backwards, we're going to have to prevent elements from mapping to the same place. That means we need f to be one-to-one. So here we go. As long as f is a one-to-one function, now we have equality. And then to prove this, let's see, proof, we have to do the subset in both directions. So first we have the first subset direction. I am going to cite my lemma that I have proven. Because why do things twice? And now we can do this direction. So we're going to say that S is an, X is an element of F pre-image of image, like this. So what does this tell us? That means X is a thing that maps to f of s. That's what it means to be in the pre-image. It means x maps to whatever set is sitting inside here. Okay. So that means that the image of x is in the image of f of s. So that's the math way of writing this right here. Okay. And then now that we have x, or f of x is in f of s, we can use the fact that f is one-to-one. We now say that x is going to be an element of s because f is one-to-one. So x is unique. So that means nobody else outside of s is going to map to the element that f of x is mapping to. So we've eliminated this problem with one-to-oneness. Okay. So now that we have x is here in s, we've got our conclusion that this guy is going to be a subset of S. And now we have subset, subset in both directions. Yeah, let's clean this up a little bit. Okay. So then you put it all together and you get that these guys are equal. Okay. And we are done. Okay. So question, what about the other order? So what I mean by the other order, I mean of the image of the pre-image of, we'll say, T, where T is a subset of B. What about that guy? Well, we get subset in the other direction. Intuition behind this. Let's say that this is our set T. Now we can talk about the pre-image of T. So things that map to T. That's going to be, let's see, so this guy is the guy we're talking about. So he came from here, or he could have come from here. So both of those guys are great candidates. However, when we look at the image of that set, we're going to say that this is going to be the color we use for the image. When we look at where this gets mapped to, it's just going to that one element. Oops. And so that's a subset of T. That's not all of T. And the reason that's happening is we're not even mapping to all of T. Okay. So again, this is a picture, not a proof. So let's go ahead. Let's do a formal proof. We're going to let Y be an element of F of pre-image T. And let's see, what are we going to say? This means we know that Y is a thing that is mapped to from a set. What set? The set that sits in here. Okay. So that means that since it's getting mapped to from this set, there has to be an element in that set that is mapping to it. There you go. So this pink turns into this line. That's what it means. Okay. So then from here, what do we know about X? Well, we know that X is in the pre-image. So that means X is a thing that maps to T. That's what it means to be in the pre-image. It wouldn't be in the pre-image if it didn't map into T. So then I can say that the image of X has got to be in T. That's how we interpret it, that pink stuff. But f of X is just Y, so Y is in T. Okay. Hopefully this is vibing with people. So now I can say, therefore, this is going to be a subset of T. And we are done with this proof. Okay. So what prevented equality in this case was there was something here. Yeah, there we go. There was something here that didn't get mapped to in T. And so when we talked about the image, so the outside layer, the image, like it wasn't getting mapped to, and so it's not going to be in the image. So in order for equality to happen here, we need to guarantee it's getting mapped to. We need F to be onto. And this is a similar vibe to what we have just done. I'm going to leave that to you. This is an exercise for you guys. Go ahead, pause the video, try and prove it, work with this. You'll thank me later. Okay. So moving on from this, let's go ahead, let's do one more example with working with this theoretically. Here's a theorem from your book that we're going to go ahead and prove. First direction isn't going to be so bad, but the backwards direction kind of has like a little bit of a nuance to it. And so I would like to talk about that nuance. Let's see. So first, we're going to start with this direction, which means we're going to let x be an element of whatever's sitting here on the left-hand side, which is f of cu. And I changed my mind. It's not going to be x. I'm going to do y because we're sitting in the image. Okay. So since y is here in the image, that means something had to map to it. So there exists an x in this set such that f of x is going to equal y. Now we can use what we know about unions. We know that x will be an element of C or x will be an element of D. So then what that means is f of x is going to be an element of f of C, or f of x is going to be an element of D, or f of D, my bad. So then y, which is equal to f of x, is going to be in their union. Okay. And then ideally, I would be able to turn all of these into if and only if statements. So I try and turn it around, and immediately there's an x sitting in that line that we haven't talked about yet, so I can't turn my steps around. Pro tip, if you've got existence happening in your proof, the chances that you can reverse your steps, very, very slim. Okay. Let's go ahead, make this a little bit smaller, give ourselves some room to work for the other direction. Okay. Now for the other direction. So we're going to let y be an element of f of C union f of D. That means that y is going to be an element of f of C, or y is going to be an element of f of D. Here's the little bit of a nuance that we're going to look at carefully. So that means that there's going to exist an x in C such that f of x is equal to y, or, the or is important, there's going to exist an x in f of D, or not in f of D, in just D. such that f of x equals y. Okay, so I said there is an x, it is in C or it's in D, and it's gonna be equal to y. And I use the same x because we have an or statement. If that was an and, this wouldn't work because I don't know that there's nothing guaranteeing that like x could be in C and in D. It might be two different elements. Maybe there's an element in C that maps to Y, and there's a different element in D that also maps to C. So this or is doing us a huge favor right now because it doesn't matter where the x lives in. It just has to be one of them. It doesn't have to be both at the same time. That's really important. I'm going to give you a problem on the worksheet for warning you right now. It's going to be an intersection. That's going to be an and. That's going to break some stuff. And your job is going to be digging through that. Don't worry. I'll be trying to guide you through it. So it'll be okay. But just a forewarning. So back to this proof. So now that we have x is in C or x is in D, that means we've got then there exists an x in the union such that f of x is going to be equal to y. So then we can say that the image of x will be in the image of this set, but f of x is just y. So y is in this set. There we go. And so the image of a union is indeed equal to the union of images. Okay. So big takeaway today. Preimages and images do not cancel each other out. There are certain conditions where they cancel each other out, and that has to do with one-to-one and onto-ness. So yeah, hopefully that was okay for everybody. We understood how to like jump back and forth using images and pre-images. It's really a question of where does this map to? Is this a thing that maps to this set? Is this a thing that will get mapped to? Ask yourself those questions and you'll be able to jump back and forth more easily. Okay. That's all I've got to say for right now. So I'll see you guys later. Bye.